Let's get it started. Did you check the email? Okay. I think my TA haven't sent an email to you. But anyway, there is another homework assignment just distributed, homework number 5. And due is in 2 weeks. The homework is due until the 2 weeks later, Monday. And it has, I think, 8 or 9 problem set, all about optimization. You are supposed to solve something, use MATLAB to plot some surfaces, as well as prove the mathematical statement. Okay? Okay. Let's continue the basics of optimization. Another mathematical definitions. In previous class, we talked about the basics, the problem itself, and what's the constraint, and the basic notation such as a feasible reason, ball, adjacency, local minimum, strict local minimum, local maximum, strict local maximum, as well as global minimum, strict global minimum, global maximum, strict global maximum. Also, the definition of differentiable function, as well as directional, the derivative, the gradient, as well as Hessian matrix, also directional derivative, and the property of the square matrix, positive definite, positive semi-definite, negative definite, negative semi-definite, and the basic definition of what the norm, mathematical norm is. It's another definition. I will talk about the sequences. And limits. Okay. Sequence is written as like this, and the sequence belongs to, it could be some n-dimensional real space, but for example, the simplest possible sequence is xk, which belongs to a real number, and this can be rewritten as x of k for short. But when you see this, it's a set and it's a sequence, and the full notation is like that. Okay, another definition is sequence x of k, which belongs to real number r, converges to it's just another notation. There, for all epsilon, which are greater than 0, and there are some large k, which is x of k minus x is less than that epsilon, or equivalently, x sub k are inside of this ball, or k which are greater than large k. That's the definition about limits. Straightforward, right? If converts to x, equivalently we write the statement like this. If k approaches to infinite, then x sub k, the limit value of the x sub k is equal to x. If, like that. Okay? This is another definition of that. It's a ball is, in previous class, we defined that this ball is the very small, infinitesimal adjacent area of the point x of radius epsilon. If your x sub k belongs to this ball, okay, that is exactly the same statement like that, right? So, if there exists a large number, large k, and every small k, if this is true, then you can say that this x sub k sequence converges to x. Right? Okay, that's this is definition. So, okay. Another thing is, if x sub k goes to infinity, or sometimes minus infinity, if for all a, and there exists some large k, x sub k is greater than this a, or for this definition, x sub k is less than or equal to large a for all sub k which is greater than k. Okay? So it is another equivalent notation. The sequence diverges to infinity if for all a, and there exists some large number k, for some small k which is greater than this large number k, or x sub k is greater than a for all a, then it diverges to infinity. It's another statement in different form. If this x sub k diverges to the minus infinity, then instead of that, you have to use this one. Okay? Having said that, it is really important to define this bounds. So, let's say there is a sequence, and we call this sequence x sub k is bounded above if there exists some large a such that x sub k is less than a for all k. Okay? For all k, x of k is less than some number, and there exists a then number, which means this sequence x of k is bounded above, right? What if we are defining bounded below? Then the format is exactly same, but this one should be like that. For all k, there exists some number a, and all element inside of the sequence is greater than this a, then we can call this sequence is bounded below. Right? Straightforward. That's another mathematical definition. By the way, can you do something here? It's not working correctly? I don't know. It is not a good idea to just turn it. Okay. Okay. And this is really, really important. X of k, is a Cauchy sequence. So, name of some famous mathematician. If for all epsilon which is greater than 0, positive 0, and there exists some large k, such that x of k minus x of m is less than this epsilon for all k and some or k and or m, which is greater than a large number. Okay, and we will discuss this Cauchy sequence in sometime later. But this is really, really important definition of a sequence. Another thing, sequence x of k, we call a sequence is non-decreasing if, non-increasing first. Non-increasing if this satisfies x of k plus 1 is less than or equal to x of k for all k. Okay? Same thing. Sequence is non-decreasing if x of k plus 1 is greater than or equal to x of k for all k. And we call sequence is monotone if a sequence is non-increasing or non-decreasing. Okay? Question? Okay. Based on this simple sequences in real space, now it's time to talk about sequences in n-dimensional space. X of k, a sequence we call converge some value x and we need this statement. If x sub k I, which means x sub k is r-dimensional number, and x sub k superscript I means ith coordinate of x sub k converges to the xi. Also is O or I. Since we are now dealing with n-dimensional number, for example, if this n is equal to 3, x, y, z, then a sequence, a point inside of this space, we can call this converges to a single point in space when we satisfy every coordinate converges to that coordinate of that point. Okay? Another definition is limit points. X is a limit point of a sequence x of k if there exist subsequence of x of k that converges to x. Okay. This is for the one-dimensional space, but definition is exactly same as n-dimensional space. X is a limit point of some sequences in R-dimensional space, and it can be equal to the nth dimension itself if there exists an infinite sequence, infinite sequence x of k, which belongs to A, converges to X. Okay. Another definition. Let a set A are in real space supremum and infimum of A. And we usually write this as supremum of A. It is defined as smallest y such that x is less than y for all x in A. Also, in another word, it's the largest limit point. If you recall the definition of this limit point, the supremum of A is exactly the same as the largest limit point of A. Infimum of A, and we write this as INFA, is the largest y such that and if you recall the definition of this limit point, this is the smallest limit point of A. Okay. Let's recall this supremum of A. There is a set in real number, right? And the definition of supremum of A is the smallest which satisfies that one. My question to you is this maximum value of A? What do you think? this y means however, among these y's, this is the smallest possible y. Is this same as the maximum value of a? Yonggyun, what do you think? Okay. Okay. These concepts are not new because in high school mathematics we already deal with this one, but in more simple way. Anyway, let's say there is a x-axis, a real number, and let's say a is defined as from 0 to 1. Okay? What is the supremum of A? Inside of X, you can pick any one that satisfies that one. However, smallest y. The supremum of A is 1. Right? If you choose 1, then all elements inside of this A is less than 1. However, this one is the smallest one you can find. Right? What is the infimum of A? 0. Right. Once again, if you choose 0, but then all x is greater than or equal to this 0, however, this is the largest value you can find to satisfy that one. So, back to my original question. This maximum value of A is equal to sub A, and minimum value of A is inf A. What do you think? It looks like it's the same, right? But let me ask this question. Exactly the same. But at this time, the A is defined like open set from 0 and 1. Until now, we talk about this closed set, which means 0 and 1 are included. But now, this 0 and 1 are not included in A. What is the sub A? 1, right. Sub A. What is inf A? 0, still same. However, is 1 maximum value of A? No, it is not included. So, it is not same. These are not same. However, in previous class, we talked about the non-existence of the optimal solution, like a maximum or infimum, the minimum, because one of the main reason was the feasible reason is not bounded. But even though it is not bounded, even though we cannot find the minimum or maximum, however, we can assume infimum and supremum. That's why we are using these kind of concepts. Okay. Okay. now it's time to talk about this open set, closed set. Okay, definition. A set A is closed if it contains all its limit point. Like this. Let's recall the definition of the limit point. So, is this open set or closed set? Open set. It does not contain the limit point. The limit point would be 1 and 0. But it does not contain those limit point inside of itself. Okay, that's the definition of the closed set. And the other one is the open set. If a set A is open, if its complement and we write this one as is closed. Complement we write usually A superscript C. If there is a the famous high school style Venn diagram, if this A, there is a set, and the rest of the other we call A complement. So if A complement is closed, then A is open set. Right? Straightforward. Okay. A point X inside of A is we call interior if there is a neighborhood of X contained in A. The neighborhood definition is the ball definition. If there is a small epsilon and centered at X, we call a ball of X with radius of epsilon is called something like that, right? So, let's call this A is let's assume this A is an open set. And let's think this point X. Is this neighborhood all inside of this A? Yeah. We can find the epsilon, smallest possible epsilon. So everything is inside of this A once again. So it is safe to say that this point is inside interior of this A. But think of a point near here. Okay, simple one first. Let's say this is a closed set. It is more easier than 0 to 1. Closed set. Is 0 interior of A? Really? Can you find smallest possible epsilon that everything inside of this epsilon is also inside of this A? No. If you choose 0, then some part in this direction cannot be included in the A. So, for this closed set, actually this 0 and 1 is not interior. But think about an open set. 0 and 1. If you choose a some value near 0, because 0, we cannot choose 0, is this interior? Yeah, because we can find this epsilon. So, in open set, all thing is inside of this A and all points are interior of an open set, but for the closed set, there is some X which is not interior of that set. Okay. Okay. This open set and closed set concept is very important. Okay? We call this A union B, and we call this A cap B or A intersection B. Okay. Union of finitely many closed set is, so what do you think? Is it closed or open? Union of closed set. Closed, right? That one, intersection of closed set is closed. And union of open set also open. Intersection of open set is open. Very important thing. A set is open is necessary and sufficient condition of all of its elements are interior point. Okay. And the last definition is function and continuity. There is a set which belongs to m-dimensional spaces, and in our own class, function is defined as a map from A to R. As long as it satisfies this, it is a function. And continuity. F is continuous at a point x bar if there for all epsilon, positive number of epsilon, and there exists a del, also positive number, if those things are satisfied, and we call this function is continuous. Is just saying, it's like that. Let's assume there is a function like this, okay? And there is x bar, right? And for very infinitesimally small delta, right? And this point also. And that one is f sub x bar, right? Okay? And the largest band of this will be epsilon, right? So for all epsilon we can think of, if we can find some delta there, if we define any value of the epsilon here. But based on that, if we find a delta, then it is continuous. Counter example. Okay. Very straightforward discontinuous function. Okay. Let's say this is x bar. Fx bar is here. Right? If you choose any epsilon there, can you find a delta which will satisfy that? If this is too complex, let's make it here. Like that. Can you find? No. Okay. That's for all the definition we have to touch before we proceed to the optimization theory. Okay, let's get started. Problem P is defined as minimization of objective function such that sorry, not R. To be more generic, we would like to write some large X where X is a sequence No, not sequence. It's a n-dimensional point. F is a map from n dimension to real, and X is open set. Usually, X is equivalent to R-dimensional real space. This is the most simple unconstrained optimization problem, right? And there is two optimality condition. One is necessary condition, the other one is sufficient condition. Necessary condition and sufficient condition. Necessary condition is something like that. If X is a local minimum of problem P, then X should satisfy something. If you can state something like in this form, if X is a minimum of problem P, then X should be something. X should satisfy something. Then this is necessary condition, right? Then what would be the sufficient conditions format? Vice versa. If X bar satisfy something, then X bar is a local minimum of problem P. That's also, I believe we all talk about this kind of necessary and sufficient condition in our high school mathematics. And as you guess, it is really hard to find this sufficient condition. But it is relatively easy to find a necessary condition. If the problem gets more complex, sometimes it is virtually impossible to use sufficient condition to actually solve the problem. And most of the time, we utilize this necessary condition and we conjecture the solution by a set of necessary conditions. Okay. Okay, so now let's look into the details of this optimality condition first of all, necessary condition for optimality of unconstrained problems. Okay. Suppose f is differentiable at x bar. If there is a vector d such that gradient of x at x bar transpose d is less than 0, then for all lambda, a positive number which is also sufficiently small, then f x bar plus d, lambda d is less than fx bar. This is theorem. In mathematics, there are many kinds of things. Axiom, lemma, theorem, and the like. We don't ask the truthness of the axiom. We believe axioms. Axioms is like the shortest distance between 2 points is a straight line, something like that. We got to admit the axiom to begin with. However, based on this axiom, this theorem, we have to prove it because it's not axiom. So it should proved before utilizing it. Okay. D is a vector with same dimension of x. And this is a really, really important form. So, let's say the quadratic function once again. We assume that f is differentiable. So, okay? Let's say this is x bar. And this x bar belongs to real number, right? And this vector d in this one-dimensional real number could be minus one direction or one direction, or this direction or that direction, right? If there is a vector d, such as, and gradient of, what's the gradient of fx? And here, the slope, right? That is the gradient. Okay? And gradient times this d is the slope times minus 1 or 1, right? Let's assume this slope is maybe 1.5. Okay? This direction, 1 times 1.5, is greater than 0. So, that's not the problem. 1.5 times minus 1 is minus 1.5. Okay? Which is less than 0. So, let's take this as our d in this case. Okay? And there are sufficiently small lambda. Very small lambda. Okay? So, x bar direction was minus 1. So, minus 1 lambda maybe around here, a little less. And those function value is always straightforward, right? Okay, let's using another example. This is x space, this is y, and there is a z axis pointing out of this board. And now we are talking about the two-dimensional. So there is a this x bar is, for example, 1.2 or something like that. Okay, and this f is a surface function. So in order to depict those kind of surface function, let's draw some contour. So let's assume the function looks like something like that. Okay? And for the simplicity purpose, let's say this has a f value of 2 at the top, 5 at the top. So this surface looks like there is two peaks like that, right? Question. This is fx. Is this vector or scalar? For that fx. Vector, right. Okay. Let's assume this is a 1.2. And can you draw this vector? I mean the vector at this point? Yep. The gradient of a surface function is the direction of the change. But according to this contour, there is no change at all in function value, right? So this vector, gradient vector are always perpendicular to this contour line. Because if you go perpendicular to this contour, you will get the most of the change. Right? Okay. So then question is, at this point, this is perpendicular. At the same time, this is perpendicular. Which one is the gradient of fx? Is it increasing direction or decreasing direction? Come on. Gradient. It's increasing direction, right? So if you plot gradient fx at x bar, this is your gradient fx. Okay? Because this is 5, and if you're going down, the values become smaller and smaller. And let's say there is a vector d. And since this is a vector, and vector multiplied to the vector is a scalar, which is a dot product. So in order to get this value, what would the direction of the d? Okay? This is vector and this is vector. What is the vector dot product? a scalar, right? And the value is the projection of the length of this B on A. And if this angle is less than 90 degree, it's gonna be a positive number. But in order to get the negative number out of this dot product, what would be the angle between these two vectors? Yeah, it should be greater than 90 degree. Okay? So, our D, to make this one true, D should be around something like that. Right? By doing this one times D, then we will get this two dot product is less than 0. And for every possible lambda, but very sufficiently small lambda, then is this true? Right. This is x bar. Right? And let's say this is D. If lambda is less than 1 and 0, what would be the lambda D? It's going to be something like this, right? So, x plus lambda D may be somewhere here, right? The function evaluation at this point is less than that point. Straightforward, right? Any question? Any question? And in this theorem, D is called a descent direction. Which means if you follow this direction, your function value will decrease. And mathematically, you guys can prove why this is true. Mathematically, this f x bar plus lambda d is evaluated as f x bar plus lambda delta transpose d. It's from Taylor expansion. A small residual of lambda d. And for that, we know this alpha x bar sub lambda d approaches 0 as lambda approaches 0. So if we rearrange it, like this, like that. Since this is less than 0 and this is approaching 0, so this is greater than 0. So if you cancel this out because it becomes a 0, this is less than 0. This one should be less than 0. So from that one, you can derive that. Okay. Based on that one, we can derive this one. Suppose f is differentiable at x bar. If x is a local minimum, then the gradient at that point is equal to 0. We can utilize this theorem to prove this one. Okay, here comes the proof. There is many other approaches to prove something, but the very simple one is to like that. If we nullify the statement like this, then very simple. For example, like this, if we could find the D, then if we move according to this direction D, we could get a lower value, right? So, if this gradient f at x bar is not 0, then if you take this as a D, if you plug that one into that once again, okay? Since there is a minus sign, this is always less than 0 because right? I mean, if we take D as this value, it's going to be this one. And we know this is not 0, so this is less than 0. Which means if we follow this direction, there is a smaller value, which is not true because this x is the minimum. Because of that, this is true. That's the end of the proof. Okay? And we call this as the first order necessary optimality condition. Very important. another theorem is, suppose that f is twice differentiable. To be more precise, I'd like to twice continuously differentiable at x bar if x is a local minimum, then gradient of fx bar is equal to 0, and Hessian matrix at x bar is positive semi-definite. Okay, proof. This part is proved by this. So, first order necessary optimality condition, this is automatically proved. So we have to focus on this part. Okay. Same approach. If Hessian matrix at x bar is not positive semi-definite, then according to the definition, there exists a direction D such that D transpose Hessian D is less than 0. The definition of positive semi-definite is for all, excluding 0, all vector, this should be greater than or equal to 0. That's the definition of a positive semi-definite. So, if this is not positive semi-definite, there exists some D such that like this. Then we have fx bar plus lambda D. It's another Taylor expansion, second order. Okay, second order Taylor expansion, which is since we already proved that part, we can just cancel this out because this is 0, right? And based on the definition, this is alpha is the higher order term in Taylor expansion. Alpha x bar lambda D will approach to 0 as lambda approach to 0. Same here. If we rearrange it, that one will rearrange like x bar lambda d minus f x bar over lambda square d transpose d plus d square right? And we first nullify, and we assume that this Hessian is not positive semi-definite, which means it's less than 0, which means this part is less than 0, and this part will become 0 as lambda approaches 0. And this is a square, so it's going to be always positive, which means the upper part should be like that. But we assume that this x bar is local minimum, so this cannot be true. It's a contradiction. So that's why this should be positive semi-definite. So, this is second order necessary optimality condition. It looks very complex, but let's go back to our high school. Let's assume there is a quadratic function. In order to the minimum value, we know that f should be 0. But we cannot tell, is this minimum or a maximum, right? If this is greater than 0, if with this 2, can you tell this is a minimum or maximum? It's a minimum, right? That is first order necessary optimality condition. A little different. But concept is exactly same. That is second order necessary optimality condition. Format is a little different, and we are talking about n-dimensional, so Hessian is positive semi-definite. Nothing is different. Okay? Question? So, you can apply this theorem like that. If the sign s changes like that, then positive Hessian is positive, no, negative semi-definite. Then, if you satisfy these two, you will know that this is the local maximum, right? Exactly same. Okay. Until now, we just showed and briefly proved that the most important first order, second order necessary optimality condition. And from this Wednesday, next class, we are going to sufficient conditions. After finding these conditions, then we will begin to tackle the real example problems. Okay, thank you.